Okay, so this is take two on this video. I had a small technical difficulty, but it's not that big a deal. This is going to be a acid and base problem where we have a weak acid and they give us the molarity, and then they just want us to find the hydronium ion concentration and the pH, and then if you know the pH, you can find the POH and the OH. And they just kind of, it's like kind of basically doing exercises in the, if you get used to doing these kind of things, it will help you become better at it. Now, at this point, I would like you to stop the video and try to do the problem, and then you can come back and we'll discuss the solution. So if you did that, you probably realized that you needed this piece of information. You can't do the problem without the Ka for acetic acid, which I always remember because it's 1.8 times 10 to the negative fifth. And it's the most, acetic acid, vinegar, is the most common weak acid. And then I always remember it because ammonia, the most common weak base, has a Kb of 1.8 times 10 to the negative fifth. So they, kind of match each other. And that's kind of, that's always made it easy for me to remember. So the first thing that we need to do is we need to set up a case statement. And so the HA, get used to seeing that. That's just the weak acid, and that's the acid together. And most of your acetic acid is going to be in that form because with this small Ka, that dissociation constant, most of it doesn't dissociate. Here's your reactant, and most of it stays in that reactant form. Very little of it, because this is so small here, very little of it forms those products, okay? And that would be your hydronium ion, because remember, acids don't activate unless you dissolve them in water, and the conjugate base. And so I can just plug in here like this, and I got 1.8 times 10 to the negative fifth, and then you'll see that I put X and X, because for every one hydronium, I also get one of the conjugate base. And that's something you need to remember. You'll never be doing this for like a 2-to-1 where you would have to worry about squares or anything like that. Ka, Kb are always just going to be, it's one hydrogen that's being either accepted or transferred off. So since it's always just one, it's always going to look like this, okay? There's never the 4x cubed variation or anything. So we plug in here, and then, okay, so what I did is I squared the x's, and then I multiplied both sides by the denominator, and then that gets me down to here. And I'm ready to take the square root of that, and then that'll get me my x, and that x is going to be my hydrogen ion concentration. And this is also, I forgot to take the square root of it last time. It was not my most shining moment. And I was like, why does the pH come out to 5.35? That's not right. Because, when you've done a lot of things with acetic acid, you've kind of realized, oh, wait a minute, it should be, it's not going to be 5.35. So I'm going to take the square root, and so 0.250, I'm just going to go 2.12 times 10 to the negative 3 equals x. That's what my calculator gave me there. And so that is, if I just sort of, again, make a H plus, OH negative, pH, POH. If I just make a 2.12 times 10 to the negative 3, I'm going to take the negative log answer. That gets me 2.67. That makes me feel a little bit better. Okay. So 2.12 times 10 to the negative 3. Okay. And then, so that's where I'm at there. I did this to find x. X is my h plus. Plug that in, take the negative log of it to get 2.67. Here, I don't know, you can do it any way you want. I don't care. Let's just go 14 minus 2.67. 10 minus 7 is 3. 9 minus 6 is 3. Borrow 11.33. That would be my POH. Because 14 minus the pH is always the POH. And then I can just go 10 raised to the negative 11.33. And that's going to be 4.67. Let's go 4.68 times 10 to the negative 12. Now, if you want to do a little check on that, I'm going to take that. Oops, it's glaring. Which is my base. And then if you multiply it by your acid, it should get very close to 1 times 10 to the negative 14. So times parenthesis 2.12 times 10 caret negative 3. Boom, boom. Yeah, and so I'm pretty comfortable with that because that's 9.9 times 10 to the negative 15th. Rounded up would be 1 times 10 to the negative 14. And since we rounded a little bit, it's going to be a little bit off, but that's so close that, those answers will work, and, that's perfectly acceptable. Now, how to make sure that, this here is a little cheat. It's just like assuming that there's not going to be any significant ionization, and usually the rule is if it's less than 5%, we can just plug that concentration right in. So this is called the 5% rule, and people know you're an operator when you know how to do the 5% rule. So all you do is you take the hydrogen ion concentration, the hydronium, 2.12 times 10 to the negative third, put it over the original solution and times it by 100. So 2.12 times 10 caret negative 3, boom, divided by 0.25, boom, times 100, and not even 1% of it is ionized. So that was just the hydrogen ion concentration we calculated over the original solution times 100 to make it a percent, and it's 0.85%, so less than 1% ionizes. So we are perfectly cool to put the 0.250 in without doing an ice chart. If you get something that is like 10% ionized or 15% ionized, then yeah, you're going to have to do an ice chart. But I don't think we do that.